So today I'll be telling you how we can use time-resolved tracking of neural activity and combine it with artificial intelligence to find tools for predicting dementia risk. Dementia is a huge burden to the individuals themselves, to their close ones, and to the society. Mild cognitive impairment, or MCI, refers to a stage between normal brain aging and clinical dementia. And it's a condition affecting currently more than 10 million people in Europe alone. With the aging population, this number is predicted to double within the next 20 years. Subjects with MCI form a particularly interesting group. We know that they are in a significantly increased risk of developing dementia, especially Alzheimer's disease, within the next 5 years. But many of them also stay stable or even get better. For trying to slow down the cognitive decline and for providing the needed support for these patients, we should find the ones in the biggest risk of progression. To this end, measurements that directly track neuronal activity can be highly informative. In Alzheimer's disease, the dysfunction at the level of neuronal communication in the brain appears to be one of the earliest changes, and it may precede the patient's clinical symptoms by several years. At the cellular level, Alzheimer's disease is characterized by accumulation of amyloid bodies outside the neurons, shown here on the left side. These amyloid bodies have a toxic effect on the neurons. They first cause neuronal hyperexcitation, but later they silence the neuronal activity. These changes in turn cause excitation-inhibition imbalance, first at the local neuronal circuits, shown in the middle, and finally they lead to changes at the brain network level, and these are considered to cause the cognitive symptoms in these patients. These kind of changes could potentially be pinpointed by electroencephalography, EEG, that measures brain's electrical activity, or by MEG, magnetoencephalography, that measures the magnetic fields produced by these same neuronal currents. While EEG measurements, shown on the left, are very cheap and widely available in the world, MEG is expensive, not that widely available, but has lots of benefits, and it's shown here on the right side of the figure. Especially, it helps to locate the activated brain areas better than EEG. The magnetic fields that are produced by the neuronal activity are not disturbed by the skull and scalp between the neurons and the measuring sensors, and thus the source locations from the brain are much easier to estimate from the measured signals than in EEG. There are also big practical differences in these measurements, both for the participants and for the measuring personnel. For MEG, the preparations take maximum 15 minutes, while preparation for example, 128-channel EEG can easily take 45 minutes and require a lot of manual work, making everybody stressed and tired. There already exists data that suggests that MEG and EEG can truly provide early markers in MCI. Regional spectral patterns of resting state activity differ between controls and MCI patients, as shown in this figure. Subsequently, Pusil and others showed in their longitudinal study that functional connectivity between different brain areas, when combined with machine learning, can actually predict very well which of the subjects suffer from a progressive disease and which do not in 3-year follow-up. At about the same time that this paper was published, Italian colleagues combined functional connectivity with genetic susceptibility to Alzheimer's disease, and they showed excellent predictive accuracy of this combination. However, we are not ready to take this to the clinical settings. When these measures have then been taken to other patient cohorts, to other countries, the results have unfortunately not generalized that well. And it has become evident that at this point we need large unified data sets for extracting the best data features from MEG and EEG, which would be generalizable and most informative of the risk in these MCI subjects. So we put up a study called AI Mind. We got funding from EU Horizon 2020 for this. We collected altogether 1,006 participants in 4 clinical centers: Helsinki, Madrid, Oslo and Rome. They all were on the MCI spectrum, some with more cognitive symptoms, some with quite mild ones. And we followed these subjects with EEG measurements for 2 years at 8-month intervals. In Finland, we also collected simultaneous MEG data from these subjects. This project has had several goals. One of the first goals has been to use machine learning in finding the EEG, MEG features that are most informative of network disturbance in these subjects. And at the next stage, we will combine this information with genetic and blood biomarkers and different kind of cognitive tests that we've also collected from these patients to form the best overall estimate of the dementia risk. This slide describes the long-term goal we would like to achieve. When the first cognitive symptoms appear in a patient, they would, in addition to clinical examination, go through an MEG or EEG measurement, and the data would be combined with the information from cognitive tests that could be conducted even with the mobile device at best, and for example with blood samples, blood biomarkers, if this appears to be the best combination for forming an early risk assessment in these patients. This information could then be used for general risk factor recommendation. We already know that even in Alzheimer's disease, when we control blood pressure, cholesterol levels, diabetes, one can already significantly slow down the progression of the disease. And importantly, we may be able to provide well-screened candidates for the future medications in the field. At the moment, we are getting new medications to Alzheimer's disease, first time after 20 years. These medications are expensive, they have lots of side effects, so we need to find the ones who benefit from these medications the most. The last subjects for this project were measured only a few months ago, so the data analysis is still ongoing. But even before we have the final results of the study, the data has already been very fruitful for many questions. For example, how stable are these measures we want to look at this patient in this patient population? We actually seldom have this size data sets to work on, and stability and replicability are clinically very valid questions. This figure demonstrates the excellent test-retest stability for the most prominent oscillatory power spectral feature, so-called alpha rhythm, both for its peak frequency and amplitude, between 2 5-minute runs while the subjects were resting with their eyes closed. This stability is also reflected as very high intraclass correlation coefficients shown in this slide. We have also asked whether using an active task in these patients, we would target the disease-relevant brain networks or cognitive domains even better and would yield even more sensitive markers than resting state data alone. There is previous evidence from EEG suggesting that abnormalities in the so-called N400 response during lexical semantic tasks would be indicative of a memory disorder. Our rather simple lexical semantic task is described in this slide. So the participants performed a task where they were asked to judge whether 2 written words were related, like banana and orange, or whether they were unrelated, banana and police. After each target word, the participants needed to make a decision and respond with a button press. We expected here that the responses to unrelated incongruent targets would be stronger than to the related congruent ones, as has been shown earlier in young healthy adults. We also assumed that this congruency effect, where the responses to unrelated target words are normally weak, would then be weaker in these participants with a developing memory disorder. We set up the project in 2 stages. Our first aim was to understand how lexical semantic processing differs between healthy young adults and healthy elderly adults in order to develop a reliable marker of this processing that would work well also in an elderly population. And our second aim was then to apply this marker to a cohort suffering from different levels of cognitive impairment, ranging from subjective memory concern to different levels of objective memory impairment. The problem in developing markers for MEG and EEG data is that the brain responses are highly individual. We therefore constructed individual machine learning models that aim to decode whether across trials a participant is seeing a related or unrelated word pair. So if the lexical semantic processing is intact in an individual, there should be information in the MEG signal such that we could decode it with high accuracy, as shown here in the upper part of the picture. And then if there's a weak effect, we should have a low decodability of this effect. Indeed, our machine learning algorithm worked quite nicely. If we look first at our healthy subjects, the decodability of the congruency effect was statistically significant in both young controls and old controls at around 400 to 600 milliseconds after the presentation of the second word. Furthermore, the congruency effect correlated with task performance. Participants who had better decodability, that is, participants with more information present in the MEG signal about the congruency, were faster, whereas participants with low decodability or weaker congruency effect were slower in performing the task. And this was true for both young and old control participants. So now we have a task that gives a nice marker of semantic processing and correlates with performance. So how about our patients with cognitive impairment? Yeah, and there is my basically last slide and our main results so far. So here you see that our preliminary decodability results in our cognitively impaired subjects are really promising. We see a clear statistically significant difference between our cognitively clearly impaired MCI plus subjects compared to SCI subjects who only have a subjective cognitive concern. The difference was further boosted by including blood biomarkers into the analysis. And again, we see a strong correlation with the task performance, such that patients with better decodability performed the task faster. So altogether, these results suggest that MEG and EEG might provide early, sensitive, and feasible biomarkers of cognitive decline. We have still a lot to do, but we are already really excited about these early results. Thank you for listening, and I also want to thank all my collaborators in this project.